Max Planck, a name etched in the annals of scientific history, emerged at a time when classical physics seemed to have reached its peak. The 19th century had seen monumental achievements, with the laws of thermodynamics and Newtonian mechanics offering explanations for many natural phenomena. Yet, as the century came to a close, physicists encountered problems that these established theories could not address. Among the most challenging of these issues was the phenomenon known as black-body radiation. For years, scientists had been unable to explain the observed behavior of radiation emitted by objects that absorbed all incoming radiation, a problem that came to be known as the ultraviolet catastrophe. The explanation demanded a shift in perspective, and it was Planck who, through his bold ideas, would pave the way for a new era in physics, an era that would ultimately give birth to quantum mechanics. Planck's initial approach to the black-body radiation problem was rooted in his deep understanding of classical physics. At the time, scientists had developed a theory called Rayleigh-Jean's law, which described how radiation emitted by a black body should behave. However, this law predicted that as the frequency of radiation increased, the emitted energy would become infinite, an absurd conclusion that did not match experimental observation. Classical physics was incapable of resolving this paradox, and the ultraviolet catastrophe seemed to signal the limitations of the current understanding of energy and matter. Planck, undeterred by this challenge, sought a solution by revisiting the basic principles of thermodynamics and electromagnetism. He was driven by the realization that classical theories of energy and heat were insufficient to explain the finer details of radiation behavior at higher frequencies. As he grappled with the problem, Planck found himself at a crossroads, where existing models seemed to break down. It was here that Planck's genius came into play. He introduced a revolutionary idea, the concept that energy could not be continuous, as had been previously assumed, but rather must exist in discrete packets. These packets of energy, he proposed, were the foundation of a new theory, one that would eventually be known as quantum theory. To understand the magnitude of Planck's breakthrough, it is essential to grasp the significance of the notion of energy quantization. Prior to Planck's work, energy was viewed as a continuous flow. This idea was deeply ingrained in classical physics, which treated energy as something that could be divided infinitely into smaller and smaller increments. Planck's hypothesis, however, suggested that energy could only be absorbed or emitted in specific amounts, or quanta. The size of each quantum of energy was determined by a constant that Planck introduced, now famously known as Planck's constant, denoted as h. This constant became one of the most fundamental quantities in all of physics, linking energy with frequency in a way that was entirely new and profound. Planck's insight into energy quantization came about through his work on the black-body radiation problem. He approached the issue from a statistical mechanics perspective, using thermodynamic principles to describe how radiation would behave in a cavity. By introducing the idea that the oscillators responsible for emitting radiation could only take on discrete energy levels, he was able to derive a mathematical expression that fit the experimental data perfectly. This marked the first time that the behavior of radiation had been explained in a way that did not lead to the ultraviolet catastrophe. The result was a formula known as Planck's radiation law that accurately described the distribution of energy across different frequencies of radiation. The success of Planck's approach was revolutionary, but what truly set it apart from other theories was its implicit suggestion that energy could not be treated as a smooth, continuous quantity. Rather, it was the quantization of energy that allowed Planck to resolve the problems with black-body radiation. His work, published in 1900, marked the birth of quantum theory and set the stage for the dramatic shifts in scientific thought that would follow in the decades to come. Although Planck's work was groundbreaking, it is important to note that he himself did not immediately recognize the full implications of his discovery. Planck initially viewed his introduction of quantized energy as a mathematical tool, a necessary step to solve the problem at hand. He did not yet grasp that the quantization of energy was not merely a convenient approximation but a fundamental feature of nature. Planck's work, while monumental, was just the beginning. The true potential of his ideas would not be fully realized until other physicists, such as Albert Einstein and Niels Bohr, extended and built upon his theories. Einstein, in particular, would take Planck's ideas to the next level. With his explanation of the photoelectric effect in 1905, by applying Planck's concept of quantized energy to light, Einstein was able to show that light itself must consist of discrete packets of energy, or photons. This was a revolutionary step forward, as it challenged the prevailing wave theory of light, which had dominated for centuries. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921 and played a pivotal role in the development of quantum mechanics. At the same time, Niels Bohr was using Planck's quantization principles to develop his model of the atom. Bohr proposed that electrons in an atom could only occupy certain discrete energy levels, a concept that directly followed from Planck's quantization of energy. Bohr's model, published in 1913, was instrumental in explaining the discrete lines observed in atomic spectra, further confirming the validity of Planck's ideas. The idea that energy levels in atoms were quantized marked another milestone in the development of quantum theory. In the years following Planck's initial work, quantum mechanics evolved rapidly, with the contributions of scientists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. These physicists expanded on Planck's ideas, developing a comprehensive framework that explained not only the behavior of radiation in atoms, but also the strange and counterintuitive phenomena that arise at the quantum level. Planck's role in this development cannot be overstated. He was the one who laid the foundation upon which the entire edifice of quantum mechanics was built. Max Planck's breakthrough was not just a mathematical solution to a technical problem. It was a paradigm shift in the way scientists thought about the nature of reality. The idea that energy could be quantized led to the realization that the classical laws of physics, which had worked so well for macroscopic systems, were inadequate for describing the behavior of matter at the smallest scales. Quantum mechanics, born from Planck's revolutionary vision, would go on to challenge our deepest assumptions about the nature of time, space, and the very fabric of the universe. What Planck accomplished in the early 20th century was nothing short of revolutionary. His work unlocked a new dimension of thought in physics, one that embraced the uncertainties and peculiarities of the microscopic world. The path that Planck set in motion would eventually lead to the development of technologies such as semiconductors, lasers, and quantum computers, all of which rely on the principles of quantum mechanics. Furthermore, Planck's work not only altered the course of physics, but also had profound philosophical implications, forcing us to reconsider our understanding of determinism, causality, and the very nature of knowledge itself. In conclusion, the birth of quantum thinking through Max Planck's revolutionary vision was one of the most significant events in the history of science. Planck's introduction of energy quantization not only solved a long-standing problem in physics, but also opened the door to an entirely new way of understanding the universe. His contributions laid the groundwork for quantum mechanics, which has since become the cornerstone of modern physics and technology. Through his vision and perseverance, Planck helped unlock the mystery of the quantum world, forever altering our view of reality. The birth of quantum theory, while pioneered by Max Planck, reached its full potential through the work of other scientists who expanded upon and refined his original ideas. Planck's initial hypothesis about energy quantization, although revolutionary, was only one part of a much larger puzzle that would eventually define the course of modern physics. His concepts, while providing a resolution to the problem of black-body radiation, set the stage for other groundbreaking discoveries in the 20th century, all of which contributed to the development of quantum mechanics. These developments were not just scientific triumphs, but also philosophical shifts in the way we understood the nature of reality. The implications of these discoveries stretched beyond physics and into areas such as technology, philosophy, and even our conception of the universe itself. The impact of Planck's work can be better understood by examining the contributions of the physicists who followed in his footsteps. One of the most significant figures in the evolution of quantum theory was Albert Einstein. In 1905, Einstein built upon Planck's concept of quantization in his explanation of the photoelectric effect. While Planck had applied the idea of energy quantization to radiation emitted by a black body, Einstein extended this idea to light itself. Einstein proposed that light, which had traditionally been understood as a wave, must also have a particle-like nature. He suggested that light is made up of discrete packets of energy, which he called photons, This was a direct extension of Planck's ideas, taking them from the realm of heat radiation and applying them to light. Einstein's theory not only solved the puzzle of the photoelectric effect, but also earned him the Nobel Prize in Physics in 1921. Einstein's work on the photoelectric effect had significant implications for the wave-particle duality of light. The concept of duality that particles, such as light, could exhibit both wave-like and particle-like properties was a cornerstone of the emerging quantum theory. This duality challenged classical physics, which had always treated particles and waves as separate phenomena. Einstein's ideas, however, paved the way for the development of quantum mechanics as a unified theory that could describe both the wave-like and particle-like behaviors of nature at the smallest scales. Another key contributor to the development of quantum mechanics was Niels Bohr, whose work on the atom built directly on Planck's ideas. In 1913, Bohr proposed his model of the hydrogen atom, in which electrons occupied discrete energy levels. Bohr's model, based on the quantization of energy levels, was an extension of Planck's hypothesis of quantized energy, applied to the behavior of electrons in atoms. According to Bohr, electrons could only orbit the nucleus of an atom at specific quantized distances, and the energy of these orbits was also quantized. This idea explained the discrete lines in atomic spectra, which had puzzled scientists for years. Bohr's model not only supported the concept of quantized energy but also provided a better understanding of atomic structure, laying the groundwork for future advancements in atomic and subatomic physics. While Bohr's work brought clarity to atomic structure, other physicists like Werner Heisenberg and Erwin Schrödinger further refined quantum theory, expanding it into a full-fledged framework. Heisenberg, in particular, introduced the uncertainty principle in 1927, which revolutionized the way we think about measurement in quantum systems. The uncertainty principle states that certain pairs of physical properties, such as position and momentum, cannot be precisely measured simultaneously. This principle arose from the wave-particle duality and highlighted the inherent limitation in our ability to know both the position and momentum of particles at the same time. Heisenberg's uncertainty principle challenged the deterministic view of the universe that had been championed by classical physics and replaced it with a probabilistic framework where outcomes were not certain but rather based on probabilities. Erwin Schrödinger, working along similar lines, developed the wave equation, which became one of the fundamental equations in quantum mechanics. Schrödinger's equation describes how the quantum state of a physical system changes over time, allows us to calculate the probability distributions for the position and momentum of particles. Schrödinger's approach emphasized the wave-like nature of particles and led to the development of quantum mechanics as a theory that could account for both the wave-like and particle-like behaviors of subatomic entities. Together with Heisenberg's uncertainty principle, Schrödinger's wave equation provided a comprehensive understanding of quantum systems, unifying the work of earlier pioneers. Max Planck's ideas also had profound implications for the development of quantum field theory, QFT, which later became one of the most important frameworks for understanding the forces of nature. QFT is the study of quantum mechanics in the context of fields such as the electromagnetic field, and it describes particles as excitations in these fields. This approach ultimately led to the development of the Standard Model of particle physics, which describes the fundamental particles and forces in the universe. Planck's ideas on energy quantization laid the groundwork for this theory, even though QFT emerged several decades after Planck's initial work. QFT has since been essential in explaining the behavior of subatomic particles and has led to the discovery of phenomena such as quantum entanglement and the Higgs boson. As quantum theory continued to evolve, it also prompted profound philosophical questions about the nature of reality itself. The uncertainty and indeterminacy inherent in quantum mechanics challenged the classical view of a deterministic universe, where everything was predictable given the initial conditions. The advent of quantum mechanics introduced the concept that, at the smallest scales, the universe is fundamentally unpredictable. This realization had far-reaching implications not only for physics but for philosophy, as it raised questions about causality, free will, and the limits of human knowledge. The famous thought experiments of Schrödinger's cat and the idea of superposition illustrated the strange and counterintuitive nature of the quantum world. In a quantum system, particles can exist in multiple states at once, and their behavior can only be described in terms of probabilities. These ideas have led to ongoing debates about the interpretation of quantum mechanics and the philosophical implications of quantum theory. Quantum theory, born out of Planck's revolutionary ideas, is the foundation for much of modern technology, from semiconductors to quantum computers. Today, quantum mechanics continues to shape our understanding of the universe and is central to fields such as materials science, quantum computing, and particle physics. The technologies that rely on quantum principles have already transformed our world and will continue to do so in the future. Planck's work, which began with the study of black-body radiation, ultimately led to the development of the quantum revolution, which has had an unparalleled impact on both science and technology. In summary, Max Planck's work laid the foundation for the birth of quantum mechanics, a theory that has not only changed the course of physics, but also revolutionized our understanding of the universe. His concept of quantized energy was the spark that ignited a series of discoveries, from Einstein's photoelectric effect to Bohr's atomic model, Heisenberg's uncertainty principle, and Schrödinger's wave mechanics. These developments have since shaped the field of quantum physics, providing us with new ways of understanding the behavior of matter and energy at the smallest scales. The influence of Planck's revolutionary vision extends far beyond the boundaries of physics, reaching into philosophy, technology, and our very conception of reality itself. Quantum mechanics, born out of Planck's vision, remains one of the most important and transformative theories in the history of science. Max Planck's contribution to the birth of quantum theory is often considered the cornerstone of modern physics, while his discovery of energy quantization in 1900 is well recognized. The impact of this theory and its evolution into a fully fledged scientific paradigm is perhaps better appreciated when examined through the lens of the developments that followed. The concept of energy quantization did not exist in a vacuum. It was the product of an environment ripe for scientific innovation, and its real power became clear only when other great minds took Planck's theories and expanded upon them. Two of the most profound contributions to this evolution came from Albert Einstein and Niels Bohr, each of whom not only applied Planck's principles to their own groundbreaking work, but also helped cement quantum mechanics as the foundation of modern physics. Albert Einstein's application of Planck's ideas to the phenomenon of the photoelectric effect in 1905 was a pivotal moment in the development of quantum theory. At the time, light was understood to be a wave, following the principles of classical physics as described by James Clerk Maxwell. According to Maxwell's equations, light should be able to exert pressure on objects, and its energy should be proportional to its intensity. However, when scientists tried to apply this understanding to the photoelectric effect, where light striking a metal surface could cause the emission of electrons, there were inconsistencies in the results. Classical wave theory could not explain why only light above a certain frequency would cause electrons to be ejected, nor could it explain the instantaneous emission of electrons upon exposure to light. Einstein, building on Planck's revolutionary insight that energy is quantized, proposed that light itself is made up of discrete packets of energy, which he called quanta. This hypothesis was radical because it suggested that light, which had long been considered a continuous wave, could also have particle-like properties. In his explanation, Einstein suggested that the energy of each photon of light is proportional to the frequency of the light, with a constant of proportionality known as Planck's constant. This was a key departure from classical physics, which had treated light purely as a wave. Einstein's work on the photoelectric effect showed that the energy of electrons emitted from a metal surface was determined by the frequency of the light, not its intensity, as had been previously thought. This was a critical breakthrough, as it validated Planck's quantization hypothesis beyond the realm of thermal radiation, and applied it to the behavior of light itself. Einstein's explanation of the photoelectric effect did more than solve a long-standing mystery in physics. It was the first major step in the development of the wave-particle duality of light, a core concept of quantum mechanics. It also provided solid experimental evidence that energy quantization was not just a theoretical construct but a real feature of the physical world. Einstein's work earned him the Nobel Prize in Physics in 1921 and set the stage for further advancements in the field of quantum theory, including the development of quantum mechanics itself. One of the most important subsequent developments in quantum mechanics came from Niels Bohr, whose work on the structure of the atom took Planck's ideas and expanded them into a model of atomic structure that explained observed phenomena. In 1913, Bohr proposed his model of the hydrogen atom, which was based on the concept of quantized energy levels for electrons. According to classical physics, electrons orbit the nucleus of an atom in continuous trajectories with no fixed position or energy. However, Bohr realized that this classical model could not explain the discrete lines observed in atomic spectra. These lines, which were emitted by atoms when they absorbed or emitted light, could not be understood if electrons were simply moving in continuous orbits. Bohr's insight was that electrons in an atom occupy only specific, quantized energy levels. These energy levels were not continuous, as classical physics would have predicted, but rather discrete. When electrons moved between these energy levels, they would absorb or emit energy in the form of light. The frequency of this light corresponded precisely to the energy difference between the two levels. Bohr's model of the atom not only explained the spectral lines of hydrogen but also introduced the idea that atomic structure is governed by quantized energy states. This idea was a direct extension of Planck's concept of quantized energy and showed how this principle could be applied to atomic systems. Bohr's model also had profound implications for the understanding of atomic behavior. Before Bohr, scientists had little understanding of why the chemical property of elements seemed to depend on the arrangement of electrons in atoms. By introducing the concept of quantized orbits, Bohr provided a framework for understanding the periodic table of elements and the chemical behavior of atoms. His model was eventually refined to include quantum mechanics, but the core idea that electrons occupy discrete energy levels in atoms remains one of the central principles of quantum theory. While Planck's quantization of energy was the first step, it was Einstein and Bohr who helped apply and expand this idea to other areas of physics. Einstein's work on the photoelectric effect showed that Planck's quantum hypothesis had far-reaching implications for the understanding of light and energy. Bohr's atomic model demonstrated that quantization was not just an abstract concept but a governing principle of atomic behavior. Together, their work laid the foundation for the development of quantum mechanics, which would later be developed into a comprehensive theory by scientists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. The significance of Einstein and Bohr's work goes beyond the theoretical advancements they made in the realm of quantum mechanics. Their contributions also marked a paradigm shift in how scientists approached the study of the natural world. Classical physics had been based on the idea of determinism, where the behavior of objects could be predicted with certainty if enough information was known about them. However, quantum mechanics, as developed by Einstein, Bohr, and others, introduced the concept of uncertainty and probability. In the quantum world, particles do not have definite positions or velocity. Instead, their behavior is described by probability distribution. This shift from determinism to probability was one of the most radical changes in the history of science and had profound philosophical implications. The probabilistic nature of quantum mechanics led to the development of concepts like Heisenberg's uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot both be precisely known at the same time. This was in stark contrast to the deterministic worldview of classical physics, where exact knowledge of one property could allow for the prediction of others. The uncertainty principle was a direct consequence of the wave-particle duality introduced by Einstein and Bohr and would become a central feature of quantum mechanics. It challenged the classical idea that the universe is fully predictable and suggested that, at the quantum level, the universe operates according to a set of probabilistic laws. In conclusion, Max Planck's discovery of energy quantization was just the beginning of a profound scientific revolution. While his work laid the groundwork for quantum theory, it was the contributions of Albert Einstein and Niels Bohr that fully realized the potential of Planck's ideas. Einstein's work on the photoelectric effect provided experimental confirmation of energy quantization and introduced the concept of wave-particle duality, while Bohr's atomic model demonstrated how quantization could be applied to atomic systems. These developments not only advanced our understanding of the physical world, but also ushered in a new era in scientific thought, where the deterministic laws of classical physics were replaced by the probabilistic laws of quantum mechanics. Together, Planck, Einstein, and Bohr shaped the course of modern physics and provided the foundation for the technologies and scientific advancements that have since transformed our world. Niels Bohr's contribution to the development of quantum theory represents one of the most significant advancements in the understanding of atomic structure. His model of the atom, developed in 1913, was a groundbreaking extension of Max Planck's idea on energy quantization. But it also introduced a radical new view of the electron's behavior in an atom. While Planck's work on quantization solved the blackbody radiation problem, Bohr's model applied the concept of quantization to the behavior of electrons in atoms. His work would lay the foundation for much of quantum mechanics and profoundly influence the way scientists think about the nature of matter. Bohr's model of the atom arose out of the need to explain the spectral lines of hydrogen, which classical physics could not account for. When atoms are heated or excited, they emit light at specific wavelengths, creating distinct lines in the spectrum. In the case of hydrogen, these lines appeared as a series of discrete colors corresponding to different energies. Classical physics, based on Newtonian mechanics and electromagnetism, predicted that the energy levels in an atom would be continuous, leading to a broad spectrum of emitted light. However, experimental observations showed that only specific, discrete lines were present. To explain this, Bohr introduced the concept of quantized energy levels for electrons in atoms. According to Bohr's model, electrons do not occupy arbitrary orbits around the nucleus, as was suggested by classical physics, but instead can only exist in specific, well-defined orbits, each with a fixed energy. These orbits were quantized, meaning the energy associated with each orbit was discrete and not continuous. When an electron jumped from one orbit to another, it would emit, or absorb, a quantum of energy in the form of light, and the frequency of the emitted light would correspond to the energy difference between the two orbits. Bohr's model not only accounted for the observed spectral lines of hydrogen, but also marked a crucial step in the development of quantum mechanics. By introducing the idea of quantized energy levels, Bohr showed that energy in an atom was not a continuous variable, as classical physics had assumed, but a discrete one. This was a direct extension of Planck's concept of quantization, which had been applied to radiation. Just as energy was quantized in the emission of light by black bodies, Bohr argued that the energy of electrons in atoms was also quantized. This represented a profound shift in how scientists understood atomic structure and energy. Bohr's model of the atom was not without its limitations. Successfully explained the spectral lines of hydrogen but could not account for the spectra of more complex atoms. Despite this, Bohr's work had a lasting impact on the development of quantum theory, influencing the work of other physicists, such as Werner Heisenberg and Erwin Schrödinger. In fact, Bohr's model was a crucial step towards the development of the more sophisticated quantum mechanical models that followed. Bohr's quantized orbits gave way to the more general concept of orbitals in quantum mechanics, which describe regions in space where electrons are likely to be found. Nonetheless, Bohr's basic idea that electrons occupy quantized energy levels remained a central feature of quantum mechanics. Bohr's contributions went beyond the realm of atomic physics. His work also introduced the concept of complementarity, which would become a cornerstone of quantum mechanics. Complementarity was the idea that different experimental setups could reveal different aspects of a quantum system, and that the full nature of the system could only be understood by combining these different observations. This principle was first proposed by Bohr in the context of wave-particle duality, a concept that was central to the development of quantum mechanics. Bohr argued that light could be understood both as a wave and as a particle, depending on the type of experiment being conducted. This idea of complementarity laid the groundwork for the development of the Copenhagen interpretation of quantum mechanics, which became one of the most widely accepted views of the quantum world. The Copenhagen interpretation, developed by Bohr and Heisenberg, is based on the idea that the act of measurement plays a fundamental role in determining the state of a quantum system. According to this interpretation, quantum systems do not have definite properties until they are measured. Prior to measurement, they exist in a state of probability described by a wave function. The wave function contains all the information about the possible states of the system, but it does not tell us the exact state until the measurement is made. This concept of wave function collapse was one of the most controversial aspects of quantum mechanics and led to ongoing debates about the interpretation of quantum theory. The implications of Bohr's work extended far beyond the realm of atomic and subatomic physics. His ideas had a profound influence on the philosophy of science, particularly with regard to the nature of reality and the limits of human knowledge. The concept of complementarity, in particular, challenged classical ideas of objective reality. According to Bohr, the nature of quantum systems could not be fully described by classical concepts of determinism and causality. Instead, quantum systems are inherently probabilistic, and their properties are only revealed through the process of measurement. This raised important philosophical questions about the nature of reality and whether the universe is fundamentally uncertain or deterministic. Bohr's work and the philosophical debates that followed would shape the course of 20th century philosophy, particularly in the areas of epistemology and metaphysics, while Planck's work laid the foundation for quantum mechanics and Einstein's contributions provided experimental validation for energy quantization. It was Bohr who gave quantum theory a solid conceptual framework for understanding atomic structure and behavior. His ideas helped turn quantum mechanics from a theoretical curiosity into a robust and coherent scientific theory. The concept of quantized energy levels and the introduction of the wave-particle duality of light were crucial steps in the development of quantum theory. Moreover, Bohr's concept of complementarity and the Copenhagen interpretation became central to the philosophical underpinnings of quantum mechanics. As quantum theory evolved, Bohr's contributions were expanded upon by other scientists, but his role in the development of the field cannot be overstated. Bohr's atomic model may have been replaced by more sophisticated quantum mechanical models, but his fundamental ideas about energy quantization and the role of measurement in quantum systems remain central to our understanding of the quantum world. Quantum mechanics, as developed by Bohr and others, has since become one of the most successful and powerful theories in the history of science, with application ranging from the understanding of atomic and subatomic particles to the development of technologies like lasers, transistors, and quantum computers. In summary, the development of quantum mechanics is deeply intertwined with the work of Max Planck, Albert Einstein, and Niels Bohr. Planck's introduction of energy quantization in 1900 was the spark that ignited the quantum revolution. Einstein's work on the photoelectric effect provided crucial experimental evidence for the quantization of energy. Bohr, building on Planck's ideas, applied quantization to atomic structure and introduced new concepts, such as the quantized energy levels of electrons, wave-particle duality, and complementarity. His contributions were instrumental in shaping the direction of quantum theory and had far-reaching implications for both science and philosophy. Through the work of Planck, Einstein, and Bohr, quantum mechanics emerged as one of the most important and transformative theories in modern physics, forever changing our understanding of the universe. The development of quantum mechanics stands as one of the most profound revolutions in the history of science, and it can be traced back to the revolutionary contributions of Max Planck, Albert Einstein, and Niels Bohr. Their work over the course of the late 19th and early 20th centuries not only reshaped the understanding of energy, light, and matter, but also set the stage for the modern technological world in which we live today. The three keynotes: Planck's introduction of energy quantization, Einstein's application of this concept to the photoelectric effect, and Bohr's atomic model, each represent pivotal moments that contributed to the formation of quantum mechanics as a cohesive theory. To understand the significance of quantum mechanics and its impact on both physics and technology, it is essential to delve into the contributions of these three men and explore how their discoveries shaped the course of science. Max Planck's contribution to quantum mechanics began in 1900 when he was attempting to resolve the problem of black body radiation. Classical physics, at the time, could not explain why the emitted radiation from a black body, a theoretical object that absorbs all radiation, did not match experimental data at higher frequencies. The classical model predicted that as the frequency of radiation increased, the emitted energy would rise to infinity, which was clearly incorrect. This problem became known as the ultraviolet catastrophe. In his efforts to solve this, Planck made a bold hypothesis. Energy is not continuous, but is instead quantized, meaning it comes in discrete, fixed amounts. Planck introduced a constant, now known as Planck's constant, denoted as h, which governed the relationship between the frequency of radiation and the energy of the emitted quanta. His groundbreaking formula explained the distribution of radiation across different frequencies, successfully resolving the ultraviolet catastrophe. However, Planck's idea of energy quantization was initially intended as a mathematical trick, a means to resolve the problem with blackbody radiation, and not as a fundamental principle of physics. Nevertheless, his work marked the first real departure from classical physics and set the stage for the future development of quantum theory. Planck's work on quantized energy was revolutionary in that it challenged the previously held view of a continuous universe. Classical mechanics had long held that energy could be transferred or transformed in a smooth, unbroken flow. By contrast, Planck's discovery introduced the idea that, at the microscopic level, energy was granular, existing in indivisible chunks. This idea, while radical at the time, would have far-reaching implications for the field of physics. It was the foundation upon which later physicists, including Einstein and Bohr, would build more comprehensive theories. Albert Einstein's work on the photoelectric effect in 1905 built upon Planck's concept of quanta energy, and this contribution marked another milestone in the development of quantum mechanics. The photoelectric effect refers to the phenomenon in which light shining on a metal surface causes the emission of electrons from the metal. Classical wave theory of light, which treated light purely as a wave, could not explain why only light above a certain frequency could cause this emission. According to classical physics, the energy of light should depend on its intensity, but experiments showed that only light of a certain frequency, regardless of its intensity, could trigger the emission of electrons. Einstein proposed that light itself was quantized and consisted of discrete packets of energy, which he called photons. Each photon carried energy proportional to the frequency of the light, with Planck's constant providing the proportionality factor. This was a radical departure from the classical wave theory of light and marked the birth of wave-particle duality, a core principle of quantum mechanics. In Einstein's theory, the energy carried by a photon was transferred to an electron, allowing it to escape from the metal surface. The photoelectric effect was one of the key experiments that confirmed Planck's idea of quantized energy. Einstein's explanation of the photoelectric effect earned him the Nobel Prize in Physics in 1921, and it was instrumental in the establishment of quantum mechanics as a fundamental theory of physics. The implications of Einstein's work on the photoelectric effect went far beyond the realm of light. His theory demonstrated that energy is not only quantized in the case of thermal radiation, as Planck had suggested, but also in the case of light itself. This marked a significant expansion of quantum theory, as it applied the idea of quantized energy to another fundamental aspect of nature, the behavior of light. The wave-particle duality that Einstein's work introduced would later become a central feature of quantum mechanics, as it showed that particles, such as light, could exhibit both wave-like and particle-like properties depending on the experimental setup. This discovery challenged classical physics, which had long held that light was either a wave or a particle, but not both. Niels Bohr's contribution to quantum theory was to extend the concept of energy quantization into the domain of atomic structure. In 1913, Bohr developed his model of the hydrogen atom, which incorporated the idea of quantized energy levels for electrons. Prior to Bohr's model, classical physics could not explain why atoms emitted light at specific wavelengths. The electromagnetic theory of light predicted that electrons in an atom would spiral into the nucleus, emitting a continuous spectrum of light. However, experimental data showed that atoms emitted discrete spectral lines instead of a continuous spectrum. Bohr proposed that electrons could only occupy certain fixed orbits around the nucleus, each corresponding to a specific energy level. The energy of an electron in an atom was quantized, meaning it could only take on specific, discrete values. When an electron moved from one energy level to another, it emitted or absorbed energy in the form of light, and the frequency of this light was proportional to the energy difference between the two levels. This model successfully explained the spectral lines of hydrogen, which had puzzled scientists for decades. Bohr's model was the first to apply the idea of quantization directly to atomic structure, and it marked a significant step toward the development of quantum mechanics. Bohr's model also introduced the concept of complementarity, which became one of the central tenets of quantum mechanics. Complementarity, as proposed by Bohr, was the idea that different experimental setups could reveal different aspects of a quantum system, and that the full nature of the system could only be understood by combining these observations. This principle was first introduced in the context of wave-particle duality, which Bohr used to explain the seemingly paradoxical behavior of light. Complementarity was one of the key philosophical insights that emerged from the development of quantum theory, as it challenged classical notions of objectivity and reality. It suggested that the nature of quantum systems could not be fully captured by any single experimental method or theoretical framework, and that the act of measurement played a fundamental role in determining the state of the system. In the years that followed, Bohr's ideas were further developed by other physicists, such as Werner Heisenberg, who introduced the uncertainty principle, and Erwin Schrödinger, who formulated the wave equation. These developments expanded Bohr's model and laid the foundation for the modern theory of quantum mechanics. However, Bohr's basic idea that electrons in atoms occupy discrete energy levels remains central to our understanding of atomic structure and behavior. The contributions of Planck, Einstein, and Bohr were instrumental in shaping the quantum revolution that would dominate the 20th century. Their work provided the framework for understanding the behavior of matter and energy at the smallest scales, and it led to the development of technologies that have transformed the world. Today, quantum mechanics forms the basis of many modern technologies, from semiconductors to lasers, and it continues to drive advances in fields such as quantum computing and quantum cryptography. The revolutionary vision of these three pioneers in quantum mechanics marked the beginning of a new era in science. Their work shattered the deterministic worldview of classical physics and introduced a new probabilistic framework for understanding the universe. Quantum mechanics, with its emphasis on uncertainty, probability, and wave-particle duality, has not only revolutionized physics, but has also had profound philosophical implications. The strange and counterintuitive nature of quantum systems has forced scientists to reconsider our conception of reality itself, leading to ongoing debates about the nature of measurement, the role of the observer, and the limits of human knowledge. In summary, the contributions of Max Planck, Albert Einstein, and Niels Bohr were pivotal in the development of quantum mechanics. Planck's introduction of energy quantization set the stage for Einstein's application of this idea to the photoelectric effect, and Bohr's model of the atom extended the concept of quantized energy to atomic structure. Their combined efforts gave rise to the field of quantum mechanics, which has since become one of the most successful and transformative theories in the history of science. Through their work, they not only revolutionized our understanding of the microcosm but also laid the groundwork for the technological advancements that define the modern world. As we delve deeper into the development of quantum mechanics, we encounter the contribution of three towering figures: Max Planck, Albert Einstein, and Niels Bohr. Their work, beginning in the late 19th century and continuing into the early 20th century, radically transformed the way we understand the physical universe. While Max Planck's quantization of energy opened the door to quantum theory, it was Albert Einstein's work on the photoelectric effect and Niels Bohr's development of the atomic model that fully established quantum mechanics as a revolutionary framework in physics. These contributions not only reshaped the world of theoretical physics but also laid the foundation for a wide array of modern technologies and opened up new dimensions of understanding in both science and philosophy. Planck's role in the birth of quantum theory is well known for introducing the idea that energy is not continuous but rather comes in discrete amounts or quanta. His work was a solution to the black-body radiation problem that had eluded classical physics. However, Planck's idea was initially a mathematical device to fit experimental data rather than a theory with broader implications. It was only after other scientists, notably Einstein, expanded on Planck's concept of quantization that its true potential as a cornerstone of a new physics became evident. The first significant expansion of Planck's quantization came in 1905 when Albert Einstein applied the concept of quanta to light. Classical physics, which treated light purely as a wave, could not explain the photoelectric effect a phenomenon where light shining on a metal surface caused the emission of electrons. Einstein proposed that light was composed of discrete packets of energy, or photons, each corresponding to a specific frequency of light. He showed that the energy of these photons was proportional to the frequency of the light, which meant that light had both wave-like and particle-like properties. This idea not only explained the photoelectric effect, but also marked the beginning of the wave-particle duality concept in quantum mechanics, where particles, such as light, could exhibit both wave-like and particle-like characteristics depending on how they were observed. Einstein's explanation of the photoelectric effect was pivotal in the development of quantum theory. It provided experimental evidence for the idea that energy is quantized, a concept that Planck had introduced years earlier. Einstein's work was instrumental in solidifying the foundation of quantum mechanics, and his ideas about light helped bridge the gap between classical and quantum physics. His contribution to quantum mechanics earned him the Nobel Prize in Physics in 1921 and marked him as one of the central figures in the quantum revolution. However, it was Niels Bohr's work on atomic structure that transformed quantum theory from a theoretical concept into a model for understanding the behavior of atoms. Bohr's model of the hydrogen atom, proposed in 1913, was an extension of Planck's quantization idea applied to electrons. In the classical model, electrons were thought to orbit the nucleus in continuous paths. However, this model failed to explain why atoms emitted light at discrete wavelengths, rather than a continuous spectrum. Bohr introduced the idea that electrons could only occupy specific, quantized orbits around the nucleus. When electrons moved between these orbits, they emitted or absorbed energy in discrete quantities, corresponding to the difference in energy between the orbits. Bohr's model was able to explain the observed spectral lines of hydrogen, a breakthrough that classical physics had failed to account for. Bohr's model of the atom was revolutionary because it introduced the idea that energy levels in atoms were quantized, similar to Planck's concept of energy quantization in radiation. This was the first major application of quantum theory to atomic structure and was instrumental in shaping the course of quantum mechanics. It also laid the groundwork for the development of the concept of wave mechanics, which would later become the dominant description of atomic and subatomic phenomena. One of Bohr's key contributions to the development of quantum mechanics was his introduction of the principle of complementarity, which became one of the cornerstones of the Copenhagen interpretation of quantum mechanics. Complementarity states that different experimental setups can reveal different aspects of a quantum system, and no single experimental method can fully capture the complete nature of a quantum system. This idea was critical in understanding wave-particle duality. For example, in some experiments, light behaves like a wave, while in others, it behaves like a particle. Bohr's principle of complementarity suggested that both descriptions were valid, but they each represented only part of the reality of the quantum system. The complementarity principle also had profound philosophical implications. It suggested that our understanding of reality is limited by the tools we use to observe it. This was a departure from classical physics, where the idea of an objective reality governed by deterministic laws could, in theory, be fully described by an observer with the proper instrument. In contrast, Bohr's complementarity emphasized the role of the observer and the importance of the act of measurement in determining the state of a quantum system. This led to a shift in how scientists and philosophers thought about the nature of knowledge and reality itself. Bohr's work was not without its controversies, especially in relation to the interpretation of quantum mechanics. The idea of a probabilistic universe, in which particles did not have definite properties until measured, was difficult to reconcile with the deterministic view of classical physics. The famous debates between Bohr and Albert Einstein during the Solvay conferences in the 1920s highlighted the philosophical divide between those who embraced the probabilistic interpretation of quantum mechanics and those, like Einstein, who believed that quantum mechanics was an incomplete theory. Einstein famously said, "God does not play dice with the universe," expressing his discomfort with the randomness and uncertainty that quantum mechanics seemed to introduce. However, despite Einstein's reservations, the probabilistic interpretation of quantum mechanics, embodied in the Copenhagen interpretation, became the dominant framework in the field. Bohr's work also paved the way for further advancements in quantum theory, particularly in the development of quantum field theory and the standard model of particle physics. The concept of quantized energy levels in Bohr's atomic model led to the later development of quantum mechanics as a unified theory of particles and fields. His insights into complementarity and the role of measurement in quantum systems also influenced the development of quantum mechanics' philosophical foundations, as well as the concept of quantum entanglement, which remain one of the most fascinating and paradoxical aspects of the theory. Quantum mechanics, as developed by Planck, Einstein, and Bohr, challenged many of the assumptions of classical physics. It introduced the idea that at the microscopic level, the behavior of particles is governed by probabilities rather than certainties. This was a radical departure from the deterministic laws of classical mechanics and led to the development of new mathematical frameworks, such as Schrödinger's wave mechanics and Heisenberg's matrix mechanics. These formulations, along with the work of Dirac and others, provided the tools to describe the behavior of particles at the quantum level. The impact of quantum mechanics extends far beyond the theoretical realm. It has had a profound influence on technology, leading to the development of innovations such as lasers, transistors, and semiconductors, all of which rely on quantum principles. The advent of quantum computing, which promises to revolutionize the field of information technology, is another example of how quantum mechanics continues to shape the future. Furthermore, quantum mechanics has led to advances in fields such as quantum cryptography, quantum teleportation, and quantum sensing, opening up new possibilities for secure communication, data storage, and scientific discovery. In conclusion, the contributions of Max Planck, Albert Einstein, and Niels Bohr to the development of quantum mechanics cannot be overstated. Planck's quantization of energy set the stage for Einstein's work on the photoelectric effect, which demonstrated that light behaves as both a wave and a particle. Bohr, in turn, applied Planck's ideas to atomic structure and introduced the concept of complementarity, which became a cornerstone of quantum theory. Their work laid the foundation for the development of quantum mechanics, a theory that has not only transformed our understanding of the microscopic world, but also had a profound impact on technology, philosophy, and the way we perceive the universe. Through their insights, these three scientists revolutionized the way we think about the nature of reality, energy, and the very fabric of existence. The birth of quantum mechanics stands as one of the most monumental revolutions in the history of science, reshaping our understanding of the universe and laying the groundwork for much of modern technology. At the heart of this revolution were four key contributions that would forever alter the trajectory of physics: Max Planck's introduction of energy quantization, Albert Einstein's application of this concept to the photoelectric effect, Niels Bohr's atomic model, and Werner Heisenberg's uncertainty principle. These breakthroughs not only addressed the fundamental mysteries of light, matter, and energy, but also set the stage for the development of quantum theory, which would eventually redefine our concepts of reality itself. Max Planck's pioneering work in the late 19th century was the first significant step toward the establishment of quantum theory. He was attempting to solve the problem of black-body radiation, where classical physics could not explain why the radiation emitted by hot objects did not match observed data at certain frequencies. Planck introduced the revolutionary idea that energy is not continuous but instead is emitted in discrete packets, or quanta. This insight led to the formulation of Planck's radiation law, which accurately described the distribution of radiation across different frequencies and successfully resolved the ultraviolet catastrophe. Planck's idea of energy quantization provided a mathematical framework that would be essential for the development of quantum mechanics. Building on Planck's work, Albert Einstein applied the idea of energy quantization to light, providing a new explanation for the photoelectric effect in 1905. Classical physics, which treated light as a wave, could not explain why only light above a certain frequency could eject electrons from a metal surface. Einstein proposed that light itself is made up of discrete packets of energy called photons. He showed that the energy of a photon is directly proportional to its frequency, with Planck's constant as the proportionality factor. Einstein's explanation of the photoelectric effect confirmed Planck's quantization hypothesis and marked the birth of wave-particle duality, where light was shown to have both wave-like and particle-like properties. This was a crucial step in the development of quantum mechanics and earned Einstein the Nobel Prize in Physics in 1921. Niels Bohr's contribution to quantum mechanics came in 1913 when he proposed a new model of the atom. Prior to Bohr, the atom was understood in classical terms, with electrons orbiting the nucleus in continuous paths. However, this classical model failed to explain the discrete spectral lines observed in atomic emission. Bohr's model introduced the idea that electrons could only occupy specific, quantized orbits around the nucleus, and when electrons moved between these orbits, they would emit or absorb energy in the form of light. Bohr's model successfully explained the spectral lines of hydrogen and marked a major step forward in the application of quantum theory to atomic structure. His work demonstrated that atomic energy levels are quantized, just as energy is quantized in radiation. Bohr's atomic model would later be refined and expanded by other quantum theories, but his basic principles remained central to the field. The fourth key development in quantum mechanics came from Werner Heisenberg, who, in 1927, introduced the uncertainty principle. The uncertainty principle is one of the most famous and philosophically significant aspects of quantum mechanics. Heisenberg's principle states that it is impossible to simultaneously know both the position and the momentum of a particle with perfect precision. The more accurately we measure one of these properties, the less accurately we can measure the other. This uncertainty is not due to limitations in measurement tools, but is inherent in the nature of quantum systems. Heisenberg's uncertainty principle challenged the classical view of a deterministic universe where particles had well-defined positions and velocities. Instead, it introduced a probabilistic framework where the properties of particles could only be described in terms of probabilities rather than certainties. This shift in perspective was one of the most profound aspects of quantum mechanics, as it suggested that, at the quantum level, the universe operates according to rules of uncertainty rather than determinism. Planck's energy quantization, Einstein's application to the photoelectric effect, Bohr's atomic model, and Heisenberg's uncertainty principle formed the foundation of quantum mechanics. Together, they represented a shift away from the classical physics that had dominated for centuries and opened up a new world of possibilities for understanding the behavior of matter and energy at the smallest scales. Quantum mechanics not only revolutionized physics but also laid the groundwork for numerous technological advancements, from semiconductors to lasers and quantum computing. The ideas introduced by these four scientists continue to influence both theoretical research and practical application today, highlighting their lasting impact on the field of physics and the broader world of science. Quantum mechanics, the branch of physics that studies the behavior of matter and energy at the smallest scales, is one of the most transformative theories in the history of science. Its foundations were laid by the pioneering work of scientists like Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. Each of these thinkers made vital contributions that shaped our understanding of the quantum world. The five keynotes: Planck's quantization of energy, Einstein's explanation of the photoelectric effect, Bohr's model of the atom, Heisenberg's uncertainty principle, and Schrödinger's wave equation are critical milestones that together form the core of quantum theory. Max Planck's work in 1900 marked the birth of quantum theory. He was grappling with the problem of black-body radiation, where classical physics failed to explain why the radiation emitted by a black body did not match experimental data at certain frequencies. To resolve this issue, Planck proposed that energy is not emitted continuously, as classical physics had assumed, but in discrete units or quanta. This concept was groundbreaking because it suggested that energy at the atomic level behaves differently than at the macroscopic scale. Planck's introduction of the Planck constant, h, was key to understanding the relationship between the energy of a quantum and the frequency of radiation. Although Planck himself did not fully embrace the broader implications of his work, his hypothesis set the stage for the revolutionary developments in quantum mechanics that would follow. In 1905, Albert Einstein extended Planck's concept of energy quantization to light, providing a solution to the photoelectric effect. Classical physics had struggled to explain why light could cause electrons to be emitted from a metal surface only if its frequency exceeded a certain threshold. Einstein proposed that light is composed of discrete packets of energy, which he called photons. The energy of these photons is proportional to the frequency of the light. By applying Planck's quantum idea to light, Einstein's explanation confirmed the validity of energy quantization, introduced the concept of wave-particle duality, where light exhibits both wave-like and particle-like properties. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921 and cemented the foundation for quantum mechanics. Niels Bohr's contribution came in 1913 when he developed his model of the hydrogen atom, which introduced the concept of quantized energy levels for electrons. Prior to Bohr, classical physics predicted that electrons in an atom would spiral inward and eventually collapse into the nucleus. This, however, did not explain the discrete spectral lines emitted by atoms. Bohr proposed that electrons orbit the nucleus in fixed, quantized orbits, and they could only transition between these orbits by emitting or absorbing specific amounts of energy. The energy of each orbit was quantized, meaning electrons could only exist in certain energy states. This model not only explained the spectral lines of hydrogen, but also laid the groundwork for the development of quantum mechanics as a theory applicable to atomic systems. Bohr's model demonstrated that quantum mechanics was not just about radiation, but also about the structure of matter itself. Heisenberg's uncertainty principle, introduced in 1927, was another key breakthrough in quantum theory. The principle states that certain pairs of properties, such as position and momentum, cannot both be precisely measured at the same time. The more accurately one of these properties is measured, the less precisely the other can be determined. This idea fundamentally challenged the deterministic worldview of classical physics, where it was assumed that all properties of an object could be known simultaneously. Heisenberg's uncertainty principle suggested that at the quantum level, nature itself is governed by intrinsic uncertainty. This was a radical departure from classical physics, which had assumed a deterministic and predictable universe. The uncertainty principle became one of the cornerstones of quantum mechanics, illustrating the inherent limits of knowledge in the quantum world. Erwin Schrödinger's contribution in 1926 with his wave equation added a new dimension to the understanding of quantum systems. Schrödinger proposed that particles, such as electrons, could be described by a wave function, which represents the probability distribution of a particle's position and momentum. Unlike classical physics, which treated particles as discrete points in space, Schrödinger's wave equation treated particles as wave-like entities, with a spread-out probability of being in multiple locations at once. This wave function provided a statistical description of particles, allowing physicists to calculate the likelihood of finding a particle in a specific state. Schrödinger's wave mechanics, along with Heisenberg's matrix mechanics, provided a comprehensive mathematical framework for quantum mechanics, offering a more complete understanding of atomic and subatomic systems. Schrödinger's work led to the development of the concept of quantum superposition, where particles can exist in multiple states simultaneously, only deciding on a particular state when measured. Planck's quantization of energy, Einstein's explanation of the photoelectric effect, Bohr's atomic model, Heisenberg's uncertainty principle, and Schrödinger's wave equation are the foundational pillars of quantum mechanics. Planck's work introduced the idea of energy quanta. Einstein extended this concept to light, and Bohr applied it to atomic structure. Heisenberg's uncertainty principle revealed the intrinsic limitations of measurement at the quantum level, while Schrödinger's wave equation provided the mathematical framework for understanding quantum systems. Together, these developments created a unified theory that transformed the field of physics and continued to shape technological advancements such as semiconductors, quantum computing, and lasers. The quantum revolution, initiated by these five key figures, not only revolutionized our understanding of the microscopic world, but also opened the door to a host of technological innovations that are still evolving today. The development of quantum mechanics marks one of the most profound revolutions in science, fundamentally altering the way we understand the universe. It started with Max Planck's work in the late 19th century and was expanded upon by other great minds, including Albert Einstein, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac. Together, their groundbreaking contributions reshaped physics and introduced a new era of scientific discovery. 6 keynotes: Planck's energy quantization, Einstein's photoelectric effect, Bohr's atomic model, Heisenberg's uncertainty principle, Schrödinger as wave equation, and Dirac's formulation of quantum field theory are essential to understanding the birth and evolution of quantum mechanics. Max Planck's introduction of energy quantization in 1900 considered the first step toward the establishment of quantum mechanics. Planck was working on the problem of black body radiation, where classical physics failed to explain why radiation emitted by hot objects did not match observed data at certain frequencies. To resolve this, Planck proposed that energy is emitted in discrete quantities or quanta. His introduction of the Planck constant, h, established the relationship between the energy of a quantum and the frequency of radiation. This was a revolutionary idea because it challenged the classical view of energy as continuous and set the stage for further developments in quantum theory. Albert Einstein extended Planck's concept of energy quantization in 1905 with his explanation of the photoelectric effect. Classical wave theory of light could not explain why only light of a certain frequency could cause the emission of electrons from a metal surface, regardless of the intensity of the light. Einstein proposed that light is composed of discrete packets of energy called photons. The energy of each photon is proportional to the frequency of light, which directly linked the properties of light to the concept of quantized energy. This was the first evidence of the wave-particle duality of light, an idea that would become central to quantum theory. Einstein's work provided experimental confirmation of Planck's hypothesis and laid the groundwork for the development of quantum mechanics. He was awarded the Nobel Prize in Physics in 1921 for this achievement. Niels Bohr's model of the hydrogen atom, proposed in 1930, introduced the idea of quantized energy levels for electrons. Classical physics had predicted that electrons would spiral into the nucleus of an atom, but this did not explain the discrete spectral lines emitted by hydrogen. Bohr proposed that electrons occupy fixed orbits around the nucleus and can only transition between these orbits by absorbing or emitting specific amounts of energy. The energy associated with each orbit was quantized, meaning electrons could only exist in certain energy states. Bohr's model successfully explained the spectral lines of hydrogen and established the idea that energy levels in atoms are quantized, a concept that had been first introduced by Planck. His model was the foundation for much of atomic theory and laid the groundwork for the development of quantum mechanics. Werner Heisenberg's uncertainty principle, introduced in 1907, was another critical breakthrough in quantum mechanics. The uncertainty principle states that it is impossible to simultaneously know both the position and momentum of a particle with absolute precision. The more accurately one of these properties is measured, the less precisely the other can be known. This principle directly challenged the deterministic worldview of classical physics, where particles were assumed to have definite positions and velocities. Heisenberg's uncertainty principle introduced a fundamental limit to measurement at the quantum level and suggested that the behavior of particles is inherently probabilistic. This was one of the most profound shifts in scientific thought, as it implied that, at the microscopic scale, certainty and predictability were replaced by uncertainty and probability. Erwin Schrödinger's wave equation, formulated in 1926, provided a mathematical framework for understanding quantum systems. Unlike classical physics, where particles were described as distinct objects, Schrödinger's equation treated particles as wave-like entities. This wave function represents the probability distribution of where a particle might be found. Schrödinger's wave equation allowed physicists to calculate the probability of a particle being in a particular state, marking the first fully quantum mechanical description of particles. The wave function, a central concept in Schrödinger's equation, provided a more comprehensive understanding of quantum systems than Heisenberg's matrix mechanics, and became the foundation for much of modern quantum theory. Paul Dirac made significant contributions to quantum mechanics with his development of quantum field theory in the 1920s. Dirac formulated the relativistic wave equation for the electron, which combined quantum mechanics and special relativity. This equation predicted the existence of antimatter, a groundbreaking concept at the time. Dirac's work laid the foundation for quantum electrodynamics, QE, the theory that describes the interaction of light and matter. His development of quantum field theory also set the stage for the creation of the Standard Model of particle physics, which describes the fundamental particles and forces in the universe. Dirac's work was instrumental in the unification of quantum mechanics with relativity leading to the development of modern theoretical physics. These 6 keynotes: Planck's quantization of energy, Einstein's photoelectric effect, Bohr's atomic model, Heisenberg's uncertainty principle, Schrödinger's wave equation, and Dirac's quantum field theory are the cornerstone of quantum mechanics, each contribution built upon the last, advancing our understanding of the microscopic world and providing a framework for future discoveries. Planck's idea of quantized energy solved long-standing problems in physics and opened the door to a new way of thinking about matter and energy. Einstein's work validated Planck's theory and introduced the concept of wave-particle duality, while Bohr's model applied quantum theory to atomic structure. Heisenberg's uncertainty principle highlighted the probabilistic nature of quantum mechanics, and Schrödinger's wave equation provided a new mathematical framework for understanding quantum systems. Finally, Dirac's quantum field theory unified quantum mechanics with relativity and led to the development of quantum electrodynamics and the Standard Model of particle physics. Together, breakthroughs form the foundation of quantum mechanics, a theory that has not only revolutionized our understanding of the physical world but also led to numerous technological advancements. From semiconductors to lasers and quantum computers, the principles of quantum mechanics continue to drive innovation and shape the future of science and technology. Through the work of these 6 visionary scientists, quantum mechanics has become one of the most successful and transformative theories in the history of physics. The development of quantum mechanics is one of the most significant scientific revolutions in history, shifting our understanding of the universe and laying the foundation for modern technology. 7 keynotes: Max Planck's energy quantization, Albert Einstein's explanation of the photoelectric effect, Niels Bohr's atomic model, Werner Heisenberg's uncertainty principle, Erwin Schrödinger's wave equation, Paul Dirac's quantum field theory, and the development of quantum electrodynamics (QED) mark the crucial milestones in the evolution of quantum theory. Max Planck's introduction of quantized energy in 1900 was the first step toward the formation of quantum mechanics. He was attempting to solve the problem of black body radiation, where classical physics failed to explain the radiation emitted by objects at certain frequencies. Planck proposed that energy is not emitted continuously, as classical physics suggested, but in discrete packets, which he called quanta. This was a radical departure from the classical idea of continuous energy. Planck introduced the constant, now known as Planck's constant, h, which related the energy of a quantum to the frequency of the radiation. Planck's work was a groundbreaking step that challenged the very notion of energy in classical physics and set the stage for future quantum discoveries. Albert Einstein's work on the photoelectric effect in 1905 expanded on Planck's concept of energy quantization. While classical physics treated light as a wave, Einstein proposed that light consists of discrete packets of energy called photons. He demonstrated that the energy of these photons is proportional to the frequency of light, which confirmed Planck's idea that energy is quantized. Einstein's explanation of the photoelectric effect resolved a long-standing mystery in physics: why only light above a certain frequency could eject electrons from a metal surface. This work laid the foundation for the concept of wave-particle duality, which became a central idea in quantum mechanics, showing that light behaves both as a wave and a particle depending on how it is observed. Niels Bohr's atomic model, proposed in 1913, applied Planck's concept of quantization to the structure of the atom. Before Bohr, classical physics had failed to explain why electrons in an atom did not spiral into the nucleus. Bohr proposed that electrons move in specific, quantized orbits around the nucleus, and these orbits correspond to discrete energy levels. When electrons jump from one orbit to another, they emit or absorb energy in the form of light, with the frequency of this light corresponding to the energy difference between the orbits. Bohr's model successfully explained the discrete spectral lines of hydrogen and was a pivotal step in the development of quantum theory, providing a framework for understanding atomic structure and behavior. Werner Heisenberg's uncertainty principle, introduced in 1927, fundamentally challenged classical physics. Heisenberg proposed that there are inherent limits to the precision with which certain pairs of properties, such as position and momentum, can be simultaneously measured. The more accurately one property is known, the less precisely the other can be determined. This principle arose from the probabilistic nature of quantum mechanics, where particles do not have definite positions and velocities until measured. The uncertainty principle shattered the deterministic worldview of classical physics and introduced a new understanding of the quantum world, where uncertainty and probability replace certainty and determinism. Erwin Schrödinger's wave equation, formulated in 1926, added a new dimension to quantum theory. While Heisenberg's uncertainty principle treated particles in terms of discrete values, Schrödinger's wave equation described particles as waves, with a wave function representing the probability of finding a particle in a particular state. Schrödinger's wave mechanics provided a more complete and mathematically rigorous framework for understanding quantum systems and helped unify various approaches to quantum mechanics. The wave equation allowed scientists to calculate the probability distributions for particles' positions, making it possible to predict the behavior of quantum systems. This development marked a significant shift in how we conceptualize matter at the atomic and subatomic levels. Paul Dirac's contributions to quantum mechanics included the development of quantum field theory in the 1920s. Dirac extended quantum mechanics to incorporate special relativity, developing the Dirac equation, which describes the behavior of relativistic electrons. His equation predicted the existence of antimatter, a groundbreaking concept that was later experimentally confirmed with the discovery of the positron, the electron's antimatter counterpart. Dirac's work laid the foundation for quantum electrodynamics QED, which describes how light and matter interact at the quantum level. His unification of quantum mechanics with relativity was a major step toward the eventual development of quantum field theory, which describes particles as excitations in underlying fields. Quantum electrodynamics, developed in the 1940s by scientists such as Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, built on Dirac's work and became the most successful quantum theory. QED describes the interaction between light, photons, and matter, electrons, and other particles. One of the most remarkable aspects of QED is its ability to make extremely precise predictions that match experimental results to an extraordinary degree of accuracy. Feynman's diagrams, which depict particle interactions, became an essential tool for visualizing and calculating quantum processes. QED's development marked the peak of quantum theory, demonstrating its immense predictive power and reinforcing its role as the cornerstone of modern physics. Planck's quantization of energy, Einstein's photoelectric effect, Bohr's atomic model, Heisenberg's uncertainty principle, Schrödinger's wave equation, Dirac's quantum field theory, and the development of quantum electrodynamics represent the major milestones in the evolution of quantum mechanics. Together, they form the foundation of a theory that has not only revolutionized our understanding of the microscopic world, but also had profound implications for the development of technology. Quantum mechanics underpins much of modern technology, including semiconductors, laser, and quantum computers, and it continues to shape the future of scientific discovery. The work of these pioneering scientists marked the beginning of a new era, one where uncertainty and probability govern the behavior of the universe at the smallest scales. Through their contributions, quantum mechanics has transformed the way we perceive and interact with the world around us.